Hi, Elena. I'd love to answer that question for you. So I've gone ahead and written all the equations that we're going to need on these three boards here. So let's go ahead and dive in. So the question tells us that we have two gases, methane and butane, both in the same container, exhibiting ideal gas behavior. So let's go ahead and use that ideal gas behavior and set up the ideal gas equation. And when we do this, we can do some quick algebra, rearrange, solve for the number of moles present. And when we do, we find that there's 0.0409 moles of total gas present. So now we were told that the density was 1.695 grams per liter. So let's go ahead and use that and solve for the mass of all of the gas present. And when we do that, we find that there's 1.695 grams of gas present. So that includes both the methane and the butane. And this is a sensical answer. So we know that the density is 1.695 grams per liter, and we also know we have 1 liter. So it would make sense that we have 1.695 grams of gas present. This checks out. So let's go to the next board. And as you can see here, the math gets a little bit more intense. We've got quite a few more equations going on here. So the first one that we have is saying x plus y is equal to 1.695. And really what this is saying is that the mass of the methane plus the mass of the butane is equal to the total mass present, which is 1.695. And so we're going to use this equation and we're going to substitute it in later. We're just setting it up now. So the next equation that we have says that the moles of methane plus the moles of butane equals the total moles present, which is kind of saying the same thing, and that makes sense, right? So what we're going to do is use the definition of molecular weight, and we're going to substitute that in for moles. So we rearrange that, we solve, we find that moles is equal to the mass divided by the molecular weight. And so now we substitute that into our equation. So we have mass divided by molecular weight of methane plus the mass divided by the molecular weight of butane is equal to the total number of moles present. So there's just one last thing that we want to do. In place of the mass, we want to go ahead and use that first equation, the x plus y equation. So we know that x is equal to the mass of the methane, and y is equal to the mass of the butane. But we want to put this into terms of one variable. So either x or y. Doesn't matter which you pick. I went with x. And so what you would do is just rearrange that equation that says y is equal to 1.695 minus x, and you plug that in place of y. So now we have x over the molecular weight, which is 16.04, plus 1.695 minus x over 58.12, which is the molecular weight of butane, is equal to 0.049. And we do some algebra, we go back to our college algebra days, and we find that x is equal to 0.285 grams of methane. Great. Now I can plug that into that first equation at the very top of the page, and I can solve for y. And I can find that y is equal to 1.41 grams of butane. Now that we know that, we've accounted for the entirety of the 1.695 grams of gas present, we can go ahead and finish up this problem. So on the next page, we're just going to do a little bit of mass percent here. So we know that the mass percent of methane and the mass percent of butane, we need to find both of those with respect to carbon. So with respect to methane, it's 12 over 16 times 100%, butane 48 over 58 times 100%, and those are our mass percents. But we want to know the mass of carbon total. So we'll take the mass percent of methane, we'll multiply it by the mass of methane that is present to find how much of that methane is carbon. We'll do the same thing for the butane, and then we just sum these together and we find the total mass of carbon present. I hope this is clear. I hope this helps you.